So this section is applications of the ideal gas law. So molar volume at STP. We've seen molar mass, right? That was the mass of a mole. Molar volume is the volume of a mole. But because we're talking about gases, we have to specify what the pressure and the temperature are. So we use what's called standard temperature and pressure, or STP, and that's 1 atmosphere, which is the same as 760 torr, and a 273, this one bothers me, 273.15 Kelvin, or 0 Celsius. STP is really useful for making comparisons between gases. Why did they pick this pressure and temperature? Well, 1 atmosphere is like regular pressure, right? So if you have something that's open to the atmosphere, or you have something that's in a flexible container that can change in size, the pressure's easy. 0 degrees Celsius is the temperature of ice water. So if you want to get your gas at 0 degrees Celsius and you don't have any fancy equipment, fill the sink with ice and water and stick your container in there and wait a little bit. There you go, 0 degrees Celsius. So the molar volume is the volume occupied by 1 mole of gas at STP. So we can calculate that. PV equals nRT. This time we're solving for N. No, we're not. We're solving for V. Solving for V again. So the volume is equal to nRT over P. And what's N? 1 mole. We're calculating its volume, so that's going to be exactly 1 mole. And then R, 0.08206 liter atmospheres per mole Kelvin. And the temperature has to be in Kelvin. See, what would happen if we use Celsius here? The volume would be 0. That wouldn't work. 273.15 Kelvin divided by the pressure, 1 atmosphere. Since we're saying this is at STP, we can assume that these are exact. So 1 times 0.08206 times 273.15 divided by 1. So the volume is 22.4. It should have 4 sig figs because of the 8206.41 liters. Most of the time, since the problems are using 3 sig figs, you'll see it as 3 sig figs. And so 224 liters per 1 mole at STP. That is only for gases, people. Only for gases. It's not true for anything else. People sometimes get very creative and stick that into places where it doesn't belong. This is a very useful conversion factor. If the gas is at STP and we have its volume and we want to know how many moles of gas, there it is. We just use this as a conversion factor. Remember that 1 mole of a gas is 6.022 times 10 to the 23rd molecules. This molar volume of a gas is true of any gas. So they're all, if you have 22.4 liters of gas at STP, it's going to have a mole of gas in it, doesn't matter what kind of gas. But those gas samples will have different masses. They have the same number of particles, but some of them have heavy particles and some of them have light particles. So here is a balloon with 22.4 liters of helium in it at STP, and xenon, 1 mole is also 22.4 liters, and methane, CH4, also 22.4 liters. But what would this balloon weigh? .003 grams. How about xenon? — 131.3. And methane would be, 12 plus 4, 16.06, 04, I think. They have the same number of particles, but these are like bowling balls compared to these, which are more like ping pong balls, right? Same number, they take up the same volume. It's a weird thing about gases. Assuming ideal behavior, which of these gas samples has the greatest volume at STP? 1 gram of hydrogen, 1 gram of oxygen, or 1 gram of argon? This is a conceptual problem. We're not supposed to have to really do math. The hydrogen. Here I have 1 mass of hydrogen molecules. The hydrogen molecules are the smallest in mass. We have an equal mass of all of these things. Argon is much heavier, so you're going to have fewer particles. This one's going to have the most particles and therefore the most volume. Does that make sense? We can calculate the density of a gas at STP. Just remember that density is mass divided by volume. Densities of gases are generally given in grams per liter instead of grams per milliliter because they're much less dense. The mass of 1 mole of gas is just its molar mass, and the volume of 1 mole at STP for any gas is 22.4 liters. So the density at STP will be the molar mass divided by the molar volume. So let's calculate the densities of helium and nitrogen. Well, the density for helium will equal the molar mass of helium divided by the molar volume. — 0.179 grams per liter. The density of nitrogen? What's the molar mass of nitrogen? Is nitrogen a diatomic element? Yeah, so multiply that by 2. That's one of those things that will mess you up throughout the semester. So nitrogen and 2 divided by 22.4 liters. 1.25 grams per liter. So nitrogen is much more dense than helium. Nitrogen is the largest component of air. And so the density of air is going to be similar to the density of nitrogen. We can see the density of helium is much less, and that's why things filled with helium, as long as they're not, too heavy. If you take like a Dutch oven or something, and you seal it up and fill it up with helium, is that going to float? No, it's made out of metal, it's super heavy. But the density difference is enough that lighter things like a balloon or even, a paper bag, it'll float with helium in it. So we can also calculate the gas density under other conditions, and the gas density will change because the volume will change if you change the pressure or the temperature. So this is what I recommend. Just keep using the density equation. It's gotten a little crooked. I'm not sure what happened to it. The density is the mass over the volume. You find the volume using a gas law. A lot of times it'll be the ideal gas law. If they don't tell you the quantity of gas, like the mass, just choose 1 mole because it's easy. So the density is directly proportional to the molar mass, and your book gives you this equation. And like I said here, this equation is valid, but it's another thing to remember. And so I don't recommend using it. You also have to remember that this capital M is not molarity, it stands for molar mass. So you can use that equation, but I'm not going to use it. Let's do an example. We'll call this the last one. Calculate the density of xenon gas at a pressure of 742 millimeters of mercury and a temperature of 45 degrees Celsius. So we got some numbers. And the question, we're looking for density. So I'm going to write these guys down. 742 millimeters of mercury, 45 degrees Celsius. Let's label those. Millimeters of mercury is at PV, N, or T. That's the pressure. And 45 degrees Celsius is T. Okay. Well, that's very nice. Calculate the density. What is density? Density equals mass divided by volume, right? Chapter 1. So what's the mass of my gas? I don't know, because they didn't tell me how much there is. Choose 1 mole. The density doesn't change whether you have a small sample, large sample. It's an extensive property. It's an intensive property. It doesn't change when you change the amount of gas. So I'm going to choose N equals 1 mole. And that'll be exactly 1 mole. Well, can I find the mass of 1 mole of xenon? Sure. Can I find the volume of 1 mole of xenon, given the pressure and the temperature? Yeah, we can do that. Of course, it's a lot easier to say. So let's tackle the volume first. Just to speed things up, I'm going to rearrange the equation. The volume is nRT over P. We've seen that multiple times. So N is 1 mole. That's exactly 1 mole. 0.08206 is still the ideal gas constant. Oops. And what's the temperature? We have to make it into Kelvin. .15. And then we're going to divide by the pressure. What unit do I need? Atmospheres. Millimeters of mercury on the bottom, atmospheres on the top. So it's the same as for torr. 1 atmosphere is 760 millimeters of mercury. 742 divided by 760. Move this over far enough. And so that is equal to 0.97632 atmospheres. Moles cancel, atmospheres cancel, kelvins cancel. This is going to give me the volume in liters. .741 liters. So that's my volume, but I still need the mass. So my volume is 26.741 liters. What's the mass of 1 mole of xenon? 131.3 grams. So the density is 4.91 grams per liter. Any questions? Yeah, we'll do that one next week.